Alright everyone, welcome to another Physics QBits video. This video is going to be focused on my advice for drawing free body diagrams for those of you who kind of struggle with this and want some way to systematize it so that it's a little easier. I have this little 4-step process that I like to do when there's a complicated free body diagram, and I think it really helps cruise through things without having to think too hard, and it'll allow you to kind of catch mistakes before they happen. So let's get right into it. Okay. So first, I want to talk a little bit about why free body diagrams are important. The idea is that when we're solving force problems, we need to use Newton's second law, right? Newton's second law is really the key to understanding how forces affect objects. Mathematically, Newton's second law says that the sum of all the forces on an object, which we call the net force, tells us something about the acceleration of the object. This part is really Newton's second law, right? The idea is if I can accurately list out all of the individual forces acting on a thing, and I add them all up, I can compute what's called the net force, right? And then the net force, by Newton's second law, is what tells us about the acceleration, or the kinematics. This way, Newton's second law allows us to connect the actual physical forces, all the FIs, to the actual kinematics that result from those forces, right? And so in plain English, let's write down the definition. Adding up all the forces on an object tells us about the object's acceleration. And so free body diagrams are really important to solving force problems because they're what allow us to keep good track of all the individual forces, these FIs on the left-hand side of the equation. If you miss a force or you have extra forces that aren't really there, then your Newton's second law equation is going to be immediately wrong and you're already in big trouble, right? You're not going to be able to accurately tell what the acceleration in any situation is. I also wanted to talk about how I categorize forces because this can be kind of useful when you're working on problems and trying to draw free body diagrams. So the first category I like to keep in mind is a category called contact forces. And these are called contact forces because they actually require physical contact. So we'll say physical contact, right? So for example, you might know about the force applied by a rope. This is what we usually call a tension, and the idea is if I have a rope attached to a thing, I can yank on it, right? And so what I'm going to have is a physical force associated with that rope being attached to something. We also know that surfaces can apply contact forces. Surfaces. For example, if my phone is sitting on a table, right, the surface of the table is going to push upwards on my phone in order to support the weight of my phone. And so we call that a normal force because it is perpendicular to the surface. The other force that a surface can apply is called friction. And this is, the force responsible for slowing things down. And notably, friction is always going to be parallel to a surface, right? And these are the only two forces that a surface can apply to something. Another contact force you may be comfortable with is just some applied external force. And this could be like my hand pushing on a thing, right? Or any kind of external thing going on. I want to emphasize once again that, right, all contact forces have to require actual physical contact. And so when you're drawing your free body diagram, what this means is you need to actually see a thing touching another thing to apply a force on the other thing, right? The other category of forces we can talk about is, as you may have guessed, the category of non-contact forces. So non-contact forces are forces that can act at a distance. For example, gravity is a non-contact force, right? You don't need two things to touch in order to apply a gravitational force on each other. For example, the Earth and the Moon. There's also another non-contact force called the electrostatic force that those of you who are studying the electricity and magnetism stuff may be more familiar with. The electrostatic force is just the force between charges, right? We know that like charges repel and opposite charges attract, and those forces don't require physical contact between the charges. And so non-contact forces are the only kinds of forces that can just appear on an object with no obvious source. Okay, so with that in mind, let's talk about the actual foolproof procedure I like to have for free body diagrams. And what we're going to do is we're going to do an example problem, and we'll kind of talk through each of the 4 steps individually and show how we can use them for a problem like this. The problem that I came up with looks something like this. There's two boxes, box A and box B, and box B is resting on box A. What we're going to do is push against box A so that the friction with the wall allows us to hold up the weight of both boxes and neither of them falls. And the goal is going to be trying to draw the free body diagram for box A using our 4-step procedure. And so I'll start by introducing our first step, which I'll say is predicting the number of forces based on contacts and non-contacts. What I mean by this is that we should be able to look at the picture and get an idea of how many forces we expect on our free body diagram, just from kind of physically what's going on here. And so what I can do is I can look at my system and I recognize that there's a surface contact here, there's a surface contact here, and there's an applied external force here, right? So if I make a little list, I know that there's two surfaces, there's one contact, and I know that if this problem is happening on Earth, there should be one non-contact force, which is gravity, right? And because surfaces can apply two forces, they can apply friction and normal force, right? I have somewhere between 2 and 4 forces for the surface contacts, one force for the one contact force, and one force for gravity. So anywhere between 4 to 6 forces. Then what I'm going to do is kind of put a little thought bubble around this so that we remember it for later. And then we can actually start on our free body diagram. So step 2 is going to be start FBD with non-contact forces. So if I draw my free body diagram on the right-hand side of the page here, I know that there is going to be a single non-contact force. Let's draw the dot in a better location. Perfect. I know there's going to be one non-contact force, right? It's just going to be gravity. These boxes aren't charged, so they're not applying an electrostatic force on each other or anything like that. And so I know that I can draw my gravitational force like this, right? Then I can add forces for contacts. So the first contact force we can notice is that we're applying an external force on this box A, right? And so because I'm on the right-hand side of box A, I must be pushing it that way. So we'll call this like the applied force. Then I can look at the other contact. So for example, box B is pushing down on box A, right? This contact is above A and below B. And so we know that there's going to be some normal force. Let's do it like this, Fn B on A. I can also think about the frictional force, right, between B and A. And because neither A or B are kind of moving laterally in this situation, there's no rubbing of the surfaces against each other. And so I expect that there should be no frictional force between these two. The last contact we need to look at is the contact between the surface of A and the surface of the wall, right? This kind of left-hand side guy here. And if I think about the direction of the wall pushing on A, right, because the wall is to the left of A, then the normal force between the wall and box A needs to be this way. I'll make this a little bit more accurate. F normal wall on A, like this, right? And in this case, for this surface, we know that if there were no friction, then this whole thing would accelerate downwards, right? And so what that means is there must be friction between A and the wall. Otherwise, this free body diagram would suggest a net force going this way, and that's definitely not correct. So we know that there's going to be a frictional force parallel to the surface, and the direction has to basically oppose gravity so that this whole setup can not fall down. And we'll call this F friction between the wall and A, something like that. And so this is really the exhaustive list of all the contacts, right? We've looked at everything that's touching the box and the one non-contact force that's present. And so this is going to be our kind of final guess for what the free body diagram looks like. And the last step I have is basically doing a sanity check where we are comparing the free body diagram with the prediction. So in this case, right, we predicted somewhere between 4 and 6 forces. Maximal, there should be 6 forces, right? But we figured out that there's no frictional force for this surface contact. And so there can only be, we expect that there should be 5 forces here. And so if I look at my free body diagram and I count 1, 2, 3, 4, 5, we're all good here, right? And so I really like this procedure because it gives us a couple of places to kind of be really careful and intentional in checking whether or not the things that we're doing make sense. First of all, right, we are specifically separating the contact and non-contact forces from each other. And so we're giving each of them kind of ample space to be examined. And I think spending a little time at the very beginning of the problem, coming up with a prediction for how many forces you expect is a really good way to kind of orientate yourself when you're starting a force problem. Okay, cool. So I think this is probably good for now. I'm going to leave you all on this page with this checklist on the kind of left-hand side of the bottom so that you have a reference. But I really encourage you to try this checklist out if you feel like you have a lot of trouble when you start problems and there's a lot of like forces going on in the free body diagram. I think this is a really, really neat way to just like make things a little bit more systematic. And so you don't have to work so much with just kind of pure intuition and think yourself into trouble. These are a nice list of specific things you can do to kind of start every force problem. Okay, I'll call it there, I think. As per usual, if you have any thoughts or questions you want me to answer, please feel free to leave those in the comment section down below, and I'll try to get to them. And also, please don't forget to like and subscribe for more free physics problem solving tips. This has been Physics Tutoring Quantized.